Hello students, welcome back. The first half of chapter 7, the analytic trigonometry, is pretty much done. Only two more topics to go, and both of them are optional topics. The first one is optional because it is relatively less important, and the second, well, it is important, but it's a bit too deep. That's why it is optional. And that one's rather significant, so I'm going to cover it in a separate video. And this one will be the easier of the two. It's usually a good idea to go from easier one first and then go progressively harder. Okay, let's move on to the identities that we are interested in for this lesson. Here we go, sum to product and then product to sum. Sum to product was a structure sine plus sine or sine minus sine, or cosine plus cosine or cosine minus cosine. We can have two different angles, but we have to have two same functions. In these cases, it is possible to express the sum or differences into products, as you can see in the right hand side. Now, the proof is relatively simple if you make one key observation. Alpha can be written as half of alpha plus beta plus half of alpha minus beta. Why? This plus beta in numerator and this minus beta in numerator will cancel each other out, and then we are going to get only 2 alpha over 2, which is of course equal to alpha. Now that we decomposed alpha into some of these two angles, we can use the sum identity for sine, and we can use the sum identity for cosine. Now let's do something similar. The beta, on the other hand, is the same as half of alpha plus beta minus half of alpha minus beta. Why? This alpha in numerator and that alpha in numerator will cancel each other out, and we're going to get beta minus of negative beta, or 2 beta over 2. Of course, that's equal to beta. Again, we have decomposed successfully. So we have first angle minus the second angle. Consequently, we have the difference formula for sine. Likewise, we can apply the difference identity for cosine. Alright, and then what do we do? Well, let's go back to original identities that we wanted to prove, and then let's add or subtract appropriately. For example, if we are interested in the first one, sine of alpha plus sine of beta, here's sine of alpha and here's sine of beta. Add these two, then what do you get? This plus cosine sine and this minus cosine sine will cancel each other out, and you're going to get only twice of sine times cosine. Isn't that what we have here? Yes, indeed. You can prove the others pretty much the same fashion. How about the number 4 here? Cosine minus cosine. Well, okay, here's cosine. And then cosine of beta. Subtract one from the other. What do you get? This cosine times cosine minus that cosine times cosine will cancel each other out. And you're going to get negative of sine times sine minus sine times sine. So you're going to get negative 2 of sine times sine, as you see over here. The other identities can be proven pretty much the same fashion. Now, one more comment, please. What if we have two different functions? For example, what if we have to do something like this? Well, the method is not unique, but one way to handle it is through this. You'll have to change these into the same function. So you can change it into either sine plus sine or cosine plus cosine. Sine of alpha plus sine of pi over 2 minus beta. Why? Because cosine of beta is the same as sine of pi over 2 minus beta. Complementary identities. Or, of course, you can change the sine of alpha into cosine of pi over 2 minus alpha and keep this cosine beta as you wish. In this particular case, I decided to use sine of alpha plus sine of pi over 2 minus beta and apply the first identity, and that works out. The rest is left to the students. And of course, you can do the same thing if you have cosine minus sine or cosine plus sine, or, well, you can think of all kind of combinations there. Now, what about product to sum identities here? Well, the proof is even easier, as a matter of fact. We don't really have to make that key observation at all. All you have to do is to apply the sum and difference identities of sine and cosine, as you see over here. And then what do you want? Depending upon what you want, we do something like this. If you want to find out what is sine alpha times sine beta, among these four identities we have here, down here, find out which one has sine of alpha times sine of beta. No, this one doesn't have it. This one does. And not this one. Oh, this one does. So second and the fourth identities have sine of alpha times sine of beta. And that's what you want. Okay, pair these two up and you can add or subtract. If you add, this sine times sine and that sine times sine will cancel each other out and disappear. That's not what we want, because we want sine of alpha times sine of beta. Instead, we have to subtract. We are going to subtract the second one from the fourth one. Then this cosine this cosine times cosine and that cosine times cosine will cancel each other out. And what do you get? We get twice of sine of alpha times sine of beta. Divide 2 away, then you're going to get precisely this. The rest can be proven pretty much the same fashion. For example, what if you want to do something like this one, the second one? No, the third one. Sine times cosine. Well, where can we find sine times cosine out of these four? The first one has it, and then the third one has it. Okay, do we add or subtract? If we add, we have these two, and then these cosine sine will cancel each other out. Good, bingo. So this part and that part will disappear. If you add them up, you're going to get twice of sine alpha times cosine of beta. If you add up this one and that one, dividing 2 away, you're going to get precisely what you wanted. You can do pretty much the same thing to the other identities too. The proof is, well, tedious but elementary. The same can be said about sum to product. Tedious, maybe, but elementary. Now, memorizing them is quite a different story. I tried, but I could never get these work. I mean, they're so similar. I mean, they look alike a lot, so it's so confusing. So I abandoned. I do not try to memorize these anymore, and I just print those out and keep those somewhere, or electronically keep those somewhere. Whenever it becomes necessary, I'll just bring those back. And I advise pretty much the same approach there. Up to triple angle identities, I memorize, but those sum and product or rotation identities, those kind of things I don't. Now, applications. Good question. Where is a good application for these kind of problems? Well, the problem is I don't. This is an example problem of our textbook. Example 9, express sine of 3x times sine of 5x as a sum of trigonometric functions. Well, it says change into sum. So let's just go over the product to sum formulas, which are right up there. And then which one is sine times sine? The last one. And just blindly apply the fourth formula you see over there and simplify. That's the solution. It's that simple. Too simple to my taste. Where is mathematical thinking? Nowhere, as a matter of fact. Just identify a formula, which is explicit, and then just blindly plug those in, simplify, that's it. I don't like this kind of problem very much. Now, If you go over to calculus 2, you will see some problems that you'll have to do something like this, change products to sum as an intermediate step to do something more significant and graphically cool. Now, I regard those kind of problems as good problems, but we still have a long way to go until calculus 2. Until then, well, we don't really have much motivation for product to sum formulas. The same goes to sum to product formulas. We have these 4 formulae here, 1, 2, 3, 4. And then we have a problem like this. Write sine of 7x plus sine of 3x as a product. Just find out appropriate formula from the previous table and then blindly apply it, simplify, that's it. Where's motivation? What kind of mathematical thinking? That's a serious problem. So I'm not really emphasizing this topic very much except for one application. This one makes a bit of a sense, so let's do that. Here, harmonic oscillation problem. 3 sine of 20x plus 3 sine of 21t in a of t times sine of omega t plus v form. This time, amplitude will change with time. Not just a, but a of t. And this kind of phenomena is called beat. And that is rather common phenomena in acoustics, physics, engineering, everywhere as a matter of fact, but you can hear this kind of phenomena a lot. Now let's make a bit of a comparison between this problem and the previous problem here in this notebook. If you have sine plus cosine and you have to change it into a single sinusoid, the key is to have the same angular frequencies so that this omega is the same one, and you can have 2 different amplitudes. In that case, what is the new amplitude? It's square root of first amplitude square plus second amplitude square, kind of like Pythagorean theorem. As a matter of fact, it is Pythagorean theorem. In this particular case, we have 3, 4, 5 triangle. We have done this in the previous video. But in the second case, we have to use completely different approach. We'll have to use this product to sum formula. What I'm going to do is to factor 3 out and then consider sine of 20t plus sine of 21t. So what do you have? Sine plus sine. And go back to those sets of formulas there. Sine plus sine, yes, this is something we are going to be using. Okay, if you do, then what do we get? Well, here it is. 3 is factored out, and sine plus sine, so we have 2 of sine of alpha plus beta over 2, and cosine of alpha minus beta over 2. Now, this alpha plus beta over 2, 20 plus 21 over 2, it is 20.5t. So that's rather big angular frequency. And the second one, 20 minus 21 over 2, that's actually negative 0.5t. But cosine function is an even function, so you can drop this negative out. What happens here is the lower frequency function is absorbed into an envelope, and we have some bouncing behavior. And here's the picture. The red graph is the graph of the function, and blue is the envelope. Plus or minus 6 cosine of 0.5t. The envelope is itself a sinusoid, and that blue part gives you the amplitude of the sound. And the red part, especially this 20.5, that is the pitch. The higher the pitch gets, then the higher it sounds, things like those. Now, because the amplitude is changing by 6 plus or minus 6 cosine of 0.5t, you're gonna get a sound kind of like kind of like this. And this is rather typical in imperfectly tuned stereo sound. And the most typical example that I usually find is propeller airplanes. Left hand side and right hand side propellers produce similar but different sounds and generate this kind of beat phenomena.